molecular weight from 33 kilodaltons to 26 kilodaltons. And we categorize from FGP1 to FGP8 depending on the molecular weight. FGP8 has most smaller molecular weight, and FGP1 is the biggest one. And so, as you know, and so there are many discussions about the surface spinning mechanism and strong binding to specific ice planes occurs on ice interface, and so like this. So, and this is protein, here is ice, and so people consider the matching between the protein and the ice. And also, this is a very recent work. So this is the FGP proteins, and they consider the matching between the regular structures and ice crystal structures. And so, already, so he mentioned about the people consider that gives Thomson effect to understand the thermal hysteresis, and some molecules are solved on interface, and then the ice crystal interface become circular like this, and so we can obtain the delta T depending on the curvature of this interface. And so, in order to obtain this kind of mechanism, and we have to consider the reversible absorption on interface. And already he mentioned about that. And so it means this one absorbs very strongly on interface. So, and it means so these proteins should be incorporated into the crystal like this. So, and also this is a summary of thermal hysteresis. So I think you know Lido said already. So, and I can skip this. So this is a model of Yoshi-Thomson, and so then you can see this is a protein. So, and you can obtain this type of a circular interface. So then, so this here is the freezing point. Below the freezing point, this interface can go through, can start to grow again. So then proteins should be incorporated into the crystal. And but ice crystal has a surface melting layer, and also interface between ice and the water is a very rough and rough interface. I mean, so that when we consider the absorption of protein, we have to consider the effect of a transition region between ice and water. And this is one example of ice crystal surface which was obtained by MD simulation, and you can see the quasar liquid layer on ice crystal surface, and so this is a very recent work. I don't know how to pronounce. Very difficult to pronounce. So, with Becky. Yes. Okay. So, and he also did some computer simulations. and he discussed about the proteins and interactions, protein interaction with ice crystal structure. And also, this is one example which was obtained by MD simulation. And my colleague Nada did this kind of simulation. And you can see here, this part is the protein, and here's the ice, and here's the water. And then, so between the interface between ice and water are very diffuse structures. So, and so diffuse structures interact with protein. So, and I think this is one of the view of interactions between ice and proteins. And also, this is an example. So, gross morphology of ice in LGP solution. And we grow ice crystal in a solution, and as a function of concentration of LGP, and in pure water we obtain the circular disk. This is a very thin circular disk, and but if we add very little amount of LGP, so you can see the facet appeared around the crystal, and then so the concentration increase, and then we can obtain this kind of hexagonal edge. And also, concentration reached to this value, we can obtain the prism-like crystal. And it's growing in the direction of the z-axis. And also, the concentration reached to this 2 milligram per ml. We obtain the spindle type structures. And then, if the structure reaches 5 milligram per ml, we obtain the needle crystal, very, very long crystal, growing, extending along the z-axis.
And all of the growth conditions in terms of temperature and whatnot.
But in this case, we don't know the temperature.
So this is a different way of changing, creating a Mackay
So, and
essentially.
Yeah, because all of those up to 0.2, the c-axis is more or less coming out, and then those are those they're all prism planes.
Yeah.
And then when you go to 0.5, it all changes.
Yeah.
Okay, so the c-axis is coming out in the lower left-hand corner for 0.2 milligrams per milliliter. The c-axis is coming out. And those are real proper prism planes.
Yeah.
And then this stellar in the previous one, for 0.01 milligrams, top row.
Top row right now.
Yes.
Stellar. Are those each prism planes that are convex into the concave into the liquid?
Points.
Yeah, I mean they're pinned at the center of the prism plane.
Okay, well, I showed another.
Is the stellar thing is during growth or it's stable?
It's still growing. Just a moment, so I can show this one. So this is much better. And this is the axis of supercooling. And this is concentration of LGP. And
so the supercooling is only for this. It doesn't. It's just for the colligative shift. So it's the difference between the temperature and the concentration of the.
So this is a bulk. This is crystal growth in a bulk water.
Okay.
So
Yeah,
and
bulk
we
water-
give supercooling temperature before starting the crystal growth.
Okay, so the axis on the bottom there is just negative temperature.
Yeah, it's a negative. So and yes, this is concentration. And so in this region we obtain the dendritic pattern like this, but a little bit different. Here, this one is very close to the dendrite in pure water.
This stellar is effectively dendrites that don't side branch.
Yes, here. Yes, that's right. Yeah. And also in this region, we obtain the polyhedral type of crystal. So then, so this is I think this is very important.
Dendrites.
Yeah. So then we can obtain this kind of diagram. So like a small crystal diagram.
Yeah.
And but other functions of supercooling and concentration in this case. And here is the dendritic, and here is stellar. And so stellar means just six branched without any side branching. And here they are polyhedral, and in this region we obtain the needle crystal. Yeah, very long needle one.
So you took the idea of the salvation shell.
So this is all with AFGP type.
In this AFGP type 8, AFGP 8.
Light, the smallest.
Smallest.
And okay, so the real dramatic change is where you get this needle for all these supercoolings.
Yep.
You get explosive growth parallel to the c-axis.
Yeah.
Okay. But that's always stable, or only under the range of supercoolings that you?
Stable? Yeah, so polyhedral is stable. So maybe this line give some hysteresis temperature.
I see. But above, where you have the dotted line and you have the needles spindle, you don't extend the boundary for stable and unstable growth. Is it just
so it's delicate.
It's part of control, right?
Yeah, it's quite difficult to control.
Okay.
Yeah, so we don't know the detail about that. And also, we try to measure the growth rate of basal plane and growth rate along the a-axis. So this is the result. And this is the growth rate along the a-axis. So, and as a function of supercooling, and the parameter give concentration. And this line give growth rate of ice in pure water. And sorry, so this is a growth rate along the c-axis, basal plane growth rate. And so, and we include protein. So then growth rate, for example, 0.01, growth rate is here. So it means growth rate increase with concentration of protein. Okay, so and here this is 0.4 milligram per ml. So and this the difference, the growth rate between here and here is very large, maybe 2 orders different.
So is the idea that because the basal plane roughens and you get macro steps forming, then you get much faster growth the more you surface.
So basal phase, the growth of basal phase is enhanced strongly. But for this axis, so this is a growth rate in pure water, and Okay, so for example, if we see this initially, so for example, at this concentration, initially with increasing supercooling, this region is a polyhedral and it's changed to the stellar, and finally we obtain the dendrite. So, and let me go back. So, and if, for example, 0.01, this is a growth rate, and but the growth shape is polyhedral in this region.
That's 8.2.
Yeah, and but at this point, growth rates jump up to this point, and this point is larger than the growth rate.
And how do
in pure water.
by the growth rate, you mean the rate of advance of the fastest growing bit of the...
Yeah. So it means, yeah.
So it's a growth rate along the dendrite tip.
Yeah, that's right, dendrite tip.
And how does that compare if you say you ask what the growth rate of the area of the crystal is?
You mean, so, what do you mean so?
So, I mean, if you took, if you tried to compare the rate of the growth of a circle versus the rate of growth of a dendritic form, you could, instead of asking what the fastest rate of growth of the fastest moving part of the interface is, you could ask what the rate of change of the area of that crystal was. For the circle, it would just be the rate of advance of the radius. But for the dendrite, you'd have some parts that are growing faster and some parts that weren't.
Yeah. So,
So you don't do that?
yeah, we don't do that. But yeah, so we can say in this region is a polyhedral. So, and growth is very slow. But when the dendritic growth started, the growth rate is enhanced in this direction. Okay. So, and anyhow, so let's go back. Okay, so here, so there are very big anisotropies between the basal phase and the prismatic phase. And that the prismatic phase is prohibited by the LGP molecules, but growth for basal phase is promoted very strongly.
Eventually.
Yeah.
Is that, sorry, I don't know if you know the answer, but is that true for all AFGP 1 through 8?
Yes, we did the same experiment. So we obtained this kind of very similar result.
Qualitatively, okay, so the fact that it's an order of magnitude difference in molecular weight.
So that is so we obtained this kind of a shape. So ice crystal in FGP or FP solution. So and here is the basal phase, and in order to obtain this kind of a shape, growth rate, the basal phase must grow faster than other interface. So and this result is meaning why this kind of a shape can appear in the solution. But we don't know why this is a very high index interface, but we don't know why this interface appears like this. At least basal phase must disappear from the growth. And also this is, I think you know that already, and this is a structure of AFGP, and so this here is the saccharoid, disaccharide, and alanine, threonine residue is one unit of FCP, and so this unit so one molecule is constructed by about 4 to 50 units. So this is a very long chain type protein molecule. So anyway, but in this study, we try to observe the absorption kinetics on ice interface. And probably our goal should be to determine the protein location during the crystal growth and the inhibition, and where protein locates during the growth surface interface or inside the crystal, and to find the absorbed species concentration on interface. And also using this result, we try to determine the binding kinetics, and that is reversible or irreversible. And in order to do this experiment, we used fluorescence confocal microscopy. And this is the same thing with this experiment. Okay. Oh, sorry. And this is our experimental apparatus. So this is a free growth in bulk solution. And we prepare this kind of a very small growth cell. And this growth cell is filled by FGP solution. And then this is a glass capillary. This is inserted into the growth cell, and this this growth cell, the temperature of this growth cell is controlled by Peltier, and we can obtain the very nice temperature regulation. So the temperature fluctuation is within the 5 millikelvin.
Where are your Peltiers?
This part. This part. So two sides. Yeah. And when we obtain the supercooled state of solution, we start the ice crystal nucleation here, like this. So then, at that time, so there are many crystal particles here, and those start to grow in the capillary, and this one grows along the capillary, and there is a growth competition can occur in the capillary, and finally only one crystals survive here. So then that crystal start to grow like this. So then we can obtain only one crystal, only one single crystal in the growth cell. And okay, so this is a way to observe the free growth in solution. This is the same thing which was used Brixman many years ago for functional nitrogen.
Just out of practically speaking, you need a geometric selection to occur so you get one crystal. So there's the ratio of the diameter of the capillary and its length for a given supercooling. Empirically, one would expect if the capillary was very short, then you might get multiple crystals. How long is that?
About 20 or 30 degrees.
And the capillary size?
Is about outside diameter is about 0.7 millimeter, and inside 0.3 or something millimeter.
Okay, so you're talking about like 100.
So this is our growth cell, and so here is the growth cell. Solution is here, and this is glass capillary. And also we can rotate glass capillary using this circular part. So if this is optical axis, then if the ice crystal appear like this, we can turn to this direction. So it's easy to observe. So and this is the microscopy, confocal microscopy, which we used. And this is Nikon. This is a very nice system. And also this is the confocal microscopy system. So and laser beam focused in this area. So then sample ice crystal grow here. So then it's possible to scan. Scanning. We have a scanning system, so then we can create a two-dimensional images. And also, this is a spectral imaging system. So we the protein with fluorescence molecules can observe using this kind of a detector. So this is the pictures, and this is this part is the glass capillary, tip of a glass capillary, and then ice crystal is growing like this now. So and if I rotate this one 90 degrees, then we can see this kind of pictures, and this is fluorescence images. And you can find this crystal has a faceted shape. And this is a ice crystal growing in pure water. So this is completely different from this type of circular disc. And also, in this, I will show the movie after this. And but I say the concentration of protein in this case. So this is only 5 microgram per ml. So this is very low concentration. And also FGP. In this case, we use the FGP 456 mixture. And LGP4 included 70% of total amount, and 5 is 26 is 10%. And the temperature is 0.05 Kelvin, minus 0.05 degrees Celsius. Okay. Very close to the melting point. So, okay, so now this interface is still growing in this case, and you can see bright line here. So what happened? So, okay, so growth is stopped, and also here, growth is completely stopped. And I will show you again. But this interface. So, and any bright line did not appear, the crystal growth continues. All right?
The angle between the two facets, that looks, now so before you get to that place, it looks like the lower angle might be right, between here, those two, and then the upper, but the angle between the first facet on the top and the one on the bottom, lower right, that doesn't seem quite right. Is that?
Yeah. That's right.
Okay.
So this is not the parallel.
Yeah.
This is tilted, actually. And also, you can see at the tip of, so this interface disappear, and then new growth step appear on this interface. So then crystal growth start again.
Okay, so it's some weird index orientation.
Yes, and this is not parallel to this line. So it means this is not exactly prismatic phase.
Let the confusion continue.
Yeah. And yes, you're right. So this line and this line is not parallel. And so angle difference is about 4 degrees. In this case, we try to measure. We measure.
Is this peculiar to this mixture you're using of 4, 5, and 6?
Yeah, mixture.
Yeah. But okay, go on.
So anyway, and this is ice in pure water, but we obtain this kind of hexagonal shape. And using this data, we try to intensity and distribution. For example, in this box. So then we can obtain this kind of profile. So this is intensity profile. So and here is inside the capillary. So there is not any proteins here, of course. And here is the inside the crystal. And here, so we can see there's a very high peak at the interface. And here's the solution, okay? But for this interface, we can obtain this kind of profile. So there's not any peak at the interface.
So then you interpret that as being that's the reason that that one kept growing and the other one stopped.
In fact, this interface is already happy interface, not rounded. So, and we cannot see any absorbed protein here, but there is an interaction with the interface and the protein already. So because this is faceted crystal, if there is not any effect of a protein, we should obtain the rounding shape. But this interface is already faceted. It means there is any interactions between.
Yeah, basically what you mean is in the absence of the protein, that would be a rounded orientation at these temperatures.
Okay. And yes, and I mentioned already, and service is modified very strongly, and also And we should consider the conformation of protein on interface. And usually this AFGP molecule has a very random structures in solution. Have this, like this. If I prepare the screen and how to say, I don't know how to say in English. And okay, so yes, this is a potato. Folding. This kind of structure. That holding structure, we don't know the holding structure can absorb on ice or not. So, and we try to observe the conformation of FGP molecules under a soft state. And also, the kinetics should be related to the conformations. And so before we mention about the conformation change, I could say finite absorption of protein. Okay, so this interface is completely stopped, but this interface is growing. So it means very new, very fresh interface appear continuously at this point. Okay, so what happens? So we analyze fluorescence intensity around this line. So then we can obtain this kind of profile. Here is this part, and maybe here is the interface. So, and this is this is not how to say. So there is some the concentration gradually changed along this line. So now you can see this part is as a tip. The fluorescence intensity is weak, and that intensity increase along this line. Right? So it means absorption never occurs immediately when new interface appear at this point.
You're saying the absorption, if it happens, takes time.
Yeah, it takes time. Yeah. That's right. Yes. And also, this interface grow in this direction, and finally, this interface disappears. Then new steps appear along this interface. Okay, so, no, this is not it. So, and anyway, yeah, I mentioned about that. So, this is a growing interface. And, but growing interface is already faceted interface. So, it means we have to consider any interaction with the protein for this growing interface.
I like this picture because I can only think in 2 dimensions, but the other pictures you showed us of row shapes before had a significant, we had those macro steps and so forth. What's the, do you know the dimension, the thickness of this?
Thickness is about in this case, 30 microns.
And the contrast looks uniform in there, or the intensity
Yeah,
looks uniform in there.
So this is very, very
uniform.
Very uniform.
You have a picture of that from the side.
Sorry?
You have a picture of that from the side.
I do?
Yeah,
Mm-hmm.
you show that. No? You didn't show the picture from the side?
But we don't have any pictures for the.
Oh, I thought you showed it before.
So that is yes. You mean this one? Ah. Yes.
This one.
Yeah.
Oh, I didn't, okay.
So very flat.
Right. I thought that was something else.
Yeah.
Okay. So it's very flat. Yeah.
And also, so now let me go to the conformation change of the protein. And if we consider AFP type 1, that is the structure of AFP type 1 has this kind of alpha helix structure. But FGP is very complicated structure in the solution. So, and I think it's quite difficult to solve on ice interface. So, and we try to obtain the FTIR spectroscopy for this for this soft proteins. So this is a system of measurement. So we prepare this kind of prism. So this is a ATR system. So and sample is prepared here, and IR beam is going into this prism, and then total reflections can occur. So then evanescent light penetrates into the sample. So then we can obtain the information from a soft protein. And so this is, we prepare the samples as a solution of FGP using a D2O solution of protein. And then so we can control the temperature of this film. And so and the temperature going down, and finally we can obtain the frozen ice sample on the on this prism. So then we try to observe, try to obtain the.
Are you using heavy water because of the index refraction?
No. No. So, the signal position interact with amide.
Is the Raman? It's the Raman?
No. IR, FTIR. So I will say about that later. And this is a system. So here is the sample. And so probably we can imagine that. So here is the ATR prism, and here is the ice sample. And after the freezing, this is the ice particle, and then there are quasi-liquid layer between ice and the prism. And this circle shows a protein. The protein, all the protein should be included in the quasi-liquid layer. So because the protein does not incorporate into the crystal. So, and some protein interact with the ice interface, and other one do not interact with the interface. So, and so for example here, so for example, the temperature go up, so then you can obtain the thicker crystalline layer, and these proteins should have a structure which is same as in solution. But these proteins absorbed on ice interface may have different structures. So, and this is one of the signal which was obtained. And so this is wave number and solvents. And this big, large peak comes from D2 ice. And so, and this line shows temperature difference. Here is 10 degree, -5, -15 degrees Celsius. And at the -10 and -5 degrees Celsius, the peak position is here, but -15 peak position shifts a little bit here. So it means the ice crystal flows, water flows to the ice crystal. So, and this shift means difference between solution, water and crystal. And also the protein signal appear here. And so if we use usually H2O, this peak appear in this area. So, and it's quite difficult to recognize between the ice signal and protein signal. So that is the reason why we use H2O. Okay. And so, and we also obtain some different peak shape depending on temperature. So using this, I skip this one. So, and so using that data, we can analyze this is the peak position, and this is the temperature. So, and the peak position of for the D2 ice. So the temperature is going down. The signal move along this line for ice crystal for water, and at -12 degrees Celsius, this peak position change suddenly to this position. So it means the freezing occurs at this temperature. And this ice crystal is heated up. This signal go up like this. And finally, it melts at around about 0 degrees Celsius. And then, depending on this result, we can analyze alpha helix contents for LDP molecule. So, and so this is a cooling system, cooling. So, but in this cooling process, water still remain liquid. And okay, so this is here the liquid, and then so liquid change to the solid. At this moment, alpha helix contents suddenly increased from here to here. And heating process, this contents keeps like this, and it's go back to the original position when the temperature reaches to melting point. So it means, so this is alpha helix content increase after the freezing of water. So,
can just what does that mean? What does the alpha helix content mean?
And there are some alpha structures in solution.
Yeah.
But and if there is not any ice crystal, and all the helix structure comes from a solution. Okay, but ice crystal appears like this, but all the proteins are included in the crystallic layer. So, and all the protein has similar structures in solution structure. So we cannot obtain any content change. But when ice crystal appeared, the content of alpha helix increased. So it means the difference is.
I see. It's just
difference is so there are some adsorptive protein in this case. So probably we can imagine that that increase amounts come from adsorptive protein. Do you agree? So that is the. So I believe that this is the first evidence for the conformation change under the adsorbed state. So, and it's quite difficult to analyze conformation in the adsorbed state. There is not any other method. So that's it's quite difficult. So, but this is, I think this is, nobody say about this. But I think this is the first data about that. Right? So, yes. And so this is here, there are FGP, and but the structure is the same as in liquid. But some G's protein adsorbed on interface has a higher content of helix, of the helix structure.
What is the size of the QLL here?
Okay. So this is the value. So this is temperature dependency of thickness. This is result for pure H2O ice, and but this is result for solution. It's increased 3 times increased.
But how it's related to? I thought this is it 1 or 2 nanometer.
Size is about 3 nanometer, less than 3 nanometer.
But this is 15, or
yeah,
or without anything fixed. So
15, yeah. So and that is sequence on the size of protein. So and we can have yes. So and this is a protein. So this is thicker than the size of a protein. Some protein is included in the crystallic layer, and some parts are adsorbed on ice interface.
I don't want to stop learning. Get something later. I'm a bit confused about the size of the QLM. So this is the imagination. So and here's the ice and here's the water, and then so protein has this kind of a structure on interface.
So then, this alpha helix structure can absorb on interface. And okay, and oh, I have to finish. And so, and finally, I can say about the density on the interface. And we try to analyze this peak. So, and using this peak, it's possible to analyze the absorption density on interface. And so I don't say the details. So this is the result. In our case, molecular spacing is about 21 nanometer. So this is very similar to your result. So and so this is your result, and AFP3, this value is 20 nanometer. And also, this is a result for type 1 AFP. In this case, spacing is about 10 nanometer. So this is a little bit old data appeared in Journal of Crystal Growth. But this is the 0.3 milligram per ml, and this is 2 milligram per ml. But in our case, concentration is very low compared with this value. And if we assume James-Thomson model, so delta T should be about 6 degrees Celsius in this case. But in our case, actual temperature is about 0.05 degrees Celsius. So this is too big compared to actual temperature. So, and what happens in this case? And now we consider the sample of protein mixture of type LGP type 4, 5, 6, and so LGP6 is 70%, and some literature says 6 is very active, but 4 and 5 is not so active. So, and we consider that. So, and if only this, sorry, I mean, 4 is active. 4 is the longer one. The longer one is active. And 5 and 6 is non-active. So, and 4 is the content of LGP4 is only 10%. So, and if these proteins are LGP4, and so this one is active to, for the pinning of interface, growing interface, and other is not active. Other is not active. So, and only these proteins are active. If we consider only these are active, this length is become longer. Okay. So, and so if we consider this effect, delta T decrease to 1.2 degrees Celsius because the distance between active one and active one is become longer.
Okay, but just to make sure, the previous, what you showed us was reversed, that it was 4, 5, 6, and 7, 20, 10%. So if you assume the same surface coverage, the argument.
So, and but we cannot say It's difficult. This is just imagination. Okay, and also, yes. So ice protein dissolved when the crystal growth started again, and okay, yes, and this interface is stopped, and but new steps appear here, and then this interface started to grow again. So then this is we analyze okay. So in this case, this is intensity, and there is a peak as an interface, and but this peak disappeared when the regrowth occurred. And also, you can see some diffusion field of protein here. So it means the regrowth, when the regrowth occurs, adsorbed protein reversibly dissolved from interface and diffuse in the solution.
And that makes you integrate the area under the curves, and
yeah,
and you can show that it's all involved.
Yeah. Mm-hmm. So and finally we can this diffusion field will disappear. So and it means the protein absorbed on interface, but the absorption is not so strong. It's possible to dissolve very easily from interface. Okay.
So do I take from that last graph that the interfacial concentration on those facets where the AFP is supposedly attaching is around twice what it is in the bulk?
Oh, here and here?
Well, there was a strong peak right on the interface.
Yeah.
Yeah.
Mm.
So the concentration at the interface is roughly twice what it is in the
Yeah,
bulk?
yeah, yeah.
Which part? The ice block?
No, the liquid bulk.
Mm. Very high.
You have a surface there, and you look at volume. So when you look at volume, you need to take everything in the volume. But when you look at surface, so it's a cut. So you need somehow to convert it, which is not.
Yeah.
So I mean, it's possible, but I don't think just.
Right.
It's basically if you take some amount of protein in solution, then you stick it to the surface. So now the distances are smaller for the same amount. Because it's sequential surface.
All right. So this is the side view, and so here is the crystal. And we try to observe the inside the crystal. And so here, this part is capillary. So of course, there's not any protein inside the capillary region. And also the brightness here and here is almost same. Okay? And we try to measure it. Yes. So, and so this capillary intensity is a capillary like this, and this intensity is completely same as inside the crystal. So it means there is not any protein inside the crystal. All the molecules, protein molecules, are rejected from crystal. So no incorporation.
Yoshi, I'm not sure what I'm seeing there. On the edge.
Edge?
Yeah, on the edge of the, yeah. Is this a kind of optic?
Yes.
I'm talking about the edge there, on the, yeah, there. On the edge.
Probably that's very
He's
difficult.
talking about the tip.
What is these two lines, the black lines?
This line?
Yeah, two lines.
So this is the crystal is this kind of. So we are looking in this direction. So maybe
The crystal has.
that is the effect of prism effect. Yeah.
Got faster.
Yeah. And laser beam, it should be
Attenuation is
reflected by the inverse. So that is. Yeah. So anyway, so protein. No protein inside the crystal. So, and I already mentioned about that. So probably this is this kind of structure, protein, and others is not, does not have, others does not have this kind of structure. And okay, so and also this is the it's possible to reject from and it's possible to detach from interface very easy. So in that means, so we say that this is reversible absorption. Okay, so and okay, so this is the last one, and maybe so this kind of a view can occur as an interface. The protein attached to the IC interface and absorbed on it, and surface diffusion can occur. And during the surface diffusion, conformation change may occur, so that those proteins can absorb strongly. So it's work to stop growth of interface. And so, but anyway, this is a very slow phenomenon. And but if the interface conformation change does not occur, and those proteins go back to the solution. So, and but we don't know this kind of process. So, and we in order to confirm this kind of view, we should do the direct observation of the one single molecule observation on interface. And maybe we can see the absorbed diffusion of absorbed protein molecule interface. All right. So this is a summary. So not so many people believe this, but anyway, we say the two-step reversible. Two-step means complete and incomplete absorption. Complete absorption is a very strong absorption, but incomplete is a weak absorption. And so there are two kinds of absorption on ice interface. And also those absorption should be reversible. Right? And okay. And also, interface concentration is very large in our case. So, and solution concentration is very low, but concentration on interface is quite high in our case. And also, protein conformation can occur on interface. And also, it depends on the Q areas. And also, so we cannot say the Gibbs-Thompson model is correct by using our data. No. Okay, that's all. So thank you very much. And one more thing. And PCI, Physics and Chemistry Ice Conference will be held in Sapporo, 5 to 10 September 2010. So we are very, very welcome. All of you visit Sapporo for this conference. Thank you very much.
Will that fish be there?
How do you think about this order?
Yeah, I'm still confused about this degree of alpha.
Alpha, yes.
Yeah. I still don't understand. If I understand the experiment, if you use ATR, you can look at the quasi-liquid layer.
Yes.
I understand from this. I mean, George Ewing did many experiments.
Yeah, that's right.
And so I understand how this works. So I understand that you can measure the quasi-liquid layer thickness, and I get all of that. But this figure here, this alpha helix content, I'm still confused about it. So let me just see if I can.
Okay.
Because what I would need to understand and compare, you tell me that it freezes at, say, minus 13. That means there's no quasi-liquid layer. And then I need to have what's this mean, this alpha helix content? Because in the bulk solution, you have some alpha helix content. I would think it would be whatever the bulk solution structure is, always. So I'm confused.
Yeah. So for example, we obtain this is a and yes, this one, for example.
Okay.
So this is the wavelength. So then we obtain this kind of profile. So this profile means, so here, for example, so this is alpha helix. Structures, and other, for example, this is for how to say different structure. But there are many kinds of structures for protein, and this is a composition of different peak like this. Okay. So, and each peak relate to the different structures, conformations of the protein. So, and when the temperature decreases, so for example, this is alpha helix peak, and alpha helix peak, only alpha helix peak change, decrease or increase is a temperature change.
Okay, so you have this mixture of AFGP 4, 5, and 6.
Yeah,
in this experiment, the concentrations the percentages are 10, 20, and 70 respectively. And so then you're saying when it freezes, the content, I mean, so if you go to your next figure, the alpha helix content, you, maybe it's not that one, it's the, keep going.
Yeah.
No,
Yes,
no,
yes.
no, the next slide.
Next slide.
That one.
Yeah.
So the alpha helix content is somehow that change in the area under that,
Yeah,
just that peak, and it increases.
Yeah.
Oh, I see. So.
Yeah. So this region is still supercooled state. And there is not any ice crystal in the layer. And the ice crystal appeared here. So then content increased.
So when freezing occurred, the area under this peak or something changed. Okay.
Yeah, and so this is ice, and protein should locate in a specific layer. If there's not any change of a conformation, so we should obtain the same content.
But there is.
Before and after the freezing.
Okay, but there is a change in content. When you freeze, and then because of thermal hysteresis, it. What I don't understand, I guess, is when you then heat up and go back to higher temperatures, the alpha helix content goes back to the pre-frozen state. So what's happening? Well, that's the part I don't understand.
It means the ice size decrease with increasing temperature.
Yeah.
The melting.
So you're melting.
So melting, so and so it means the interface area also decrease with increasing.
Oh, I see. Oh, okay.
So and
I get it.
and proteins interacting with the interface decrease.
I see.
So and it means so this bleeding may occur.
So you're saying that, now I don't remember which one it was, you're saying which one of 4, 5, and 6 now is the alpha helix? Which one of those?
4.
4. And in this experiment you had it set 70% of the total solution was 4? Or in this experiment was it 10%?
10%.
Oh.
Yeah. 6, 10%, yeah.
I see. So you're saying it's strongly attracted to the surface.
Right. It's too complicated.
Yeah.
Yeah.
Okay. Okay. I understand now. I understand how you're interpreting your figure. Anyways.
Yeah.
I'm not sure I understand it.
Yeah. Yeah, we could obtain this kind of data, but we considered for a long time so how to explain this. Finally,
what I have trouble with is that in other experiments of yours and Ido's and other people's, there's a certain orientational preference, and I guess in this polycrystalline ice film that you're making, the way ATR works is that you're averaging over all the orientations. So on average, you're saying that more of 4 is adsorbed to the surface of the ice. All right. If you say so.
Yeah, but this is not still direct evidence. So, but anyhow, so I think this is the first discussion about the conformation change under the absorbed state. No what to say.
Yeah, that part I have trouble understanding is what confirmation means, because what you're showing us is that the peak area changes, so the percentage of your signal that is associated with that protein changes, but you're not measuring the actual conformation of the protein. You're just saying that it's adsorbed to the surface. Is that?
We cannot recognize the absorbed and non-absorbed proteins. We can only obtain the mixtures data.
Okay.
Yeah.
So in the slide that you talk about the mechanism, the pulsar mechanism, you show two options, alternative options. One is basically within the absorption inhibition, but only partial of the protein play a role, and this is, I think, more or less in line with what I discussed about the Stanson model. It's almost the same. But the other one, you have it completely different. I think this one. Yeah. So you suggested there's two different ideas. What is the second one?
We wanted to say. So this is here. There's a transition layer between ice and water, and diffuse layer. So the interface is diffuse. So has a diffuse structure.
Okay.
So, but it's quite difficult to say something. So and don't worry. So this image is to be.
So, but this one, the upper one is, just to my taste, is look like the absorption inhibition model.
Yeah, basically.
But it looks like it. But I guess what he's saying is that from the ATR, FTIR measurements, you understand that, or you interpret that even though your mixture has only 10% of the alpha helix structure, that's the active one on the surface. So it's simply that those are the ones that are doing the Gibbs-Thompson effect in the top picture, and the rest are sort of passive. But in fact, then well, I should let him speak for himself.
Well, then if you go to the whole rest of the
If this model is correct, molecular spacing reach become 45 nanometers. So, but still delta T is.
So according to what you said,
bigger.
when you have another growing layer, so those that stick strongly stay behind, and all the rest washed. This is what you're saying?
Yeah, the gray ones aren't really playing.
Right, but then that means that the red ones stay behind?
No, we cannot see any proteins inside the crystal after E-growth site. So, and probably all the molecules are dissolved. That's all. And there are some.
Are you envisioning when the growth occurs? Are you envisioning that there's a kind of AFGP functional segregation coefficient, so that this is a steady state picture, for example, for growth. I guess the question is, what if they're not? If you never get anything inside the crystal, then AFGP4 is more has more affinity for the surface of the ice, which you interpret from the FTIR, ATR measurements, but it doesn't ever go into the crystal, and it's sitting on the surface. Then what's happening during growth? Because your other images show that you have no concentration inside of the crystal, so it's building up on the surface. Everything's being rejected, but you want to say that only a fraction of the rejected AFGP is contributing to the thermal hysteresis effect. I'm just trying to ask the question in a different way. Is that what your question is, Ido?
I think so.
Because, yeah. Or is it just that if you only have a certain fraction, which is in this case 10% active on the surface, as long as you get to a critical concentration, you can pin the surface, and then otherwise you have to wait until that concentration gets big enough and then it pins the surface, but it never gets trapped. Okay, are you satisfied? This is your question.
Yeah.
Still not sure. But
Anyway, so our result is completely different.
Yeah.
But this is a FGP, but in this case, type of protein is different.
Okay, I could suggest that. I think it would be healthy if these two guys stayed. I'll go get the boxing. Anyway, box for a while. And
I'll go get the beer.
we'll come back, open the door later.